The dispersive networking solutions represent a new era of cybersecurity. Dispersive eliminates the traditional single path version of a VPN that is susceptible to increased security threats through exposed public IPs and open firewall ports, choppy performance, as well as packet loss and latency. Our radically different cloud native approach to virtual networking delivers new levels of security, reliability, and performance and provides a foundation for innovation and transformation across industry verticals. Inspired by battlefield proven wireless radio techniques, the Dispersive platform dynamically splits session level IP traffic at the device, edge, or cloud into smaller, independent, and individually encrypted packet streams. In today's demo, we will do a direct comparison between a traditional IPsec VPN environment and a dispersive environment. For both scenarios, we'll use an AWS-based deployment. For our IPsec VPN solution, we've deployed an OpenVPN client in the AWS US East region and an OpenVPN server in the AWS US West region. There will be a static nailed-up VPN tunnel between the two locations. On the dispersive side, we similarly have dispersive nodes deployed in AWS US East and AWS US West, with the addition of data deflects spread throughout the United States. We have a couple of deflects deployed in the AWS cloud itself, as well as bare metal-based deflects deployed in San Jose, Los Angeles, and Atlanta. Instead of a static nailed-up connection, the dispersive protocol will split the data and use multiple active-active channels to form one single session of data transport. In the case that something happens with one of these channels, for example, in the Atlanta region, we can roll that data directly to another channel without losing the overall performance of the session and continue to have the data transmit seamlessly. For the purpose of today's demo, we will demonstrate data flow in both systems using a 100 megabyte file transfer from the West Coast server to the East Coast clients. On the right-hand side, for the industry benchmark VPN, we'll use a tool called EtherApe to do packet visualization. As I start the file transfer in both systems, you can notice the EtherApe window showing all packets on the VPN side moving from the singular WAN link to the VPN server through a single tunnel. On the dispersive side, we have 6 available deflects that can be used in this system, a combination of bare metal data center deflects and AWS cloud-based deflects. I'll use the orchestrator tool to visualize exactly what's happening with the data flow in the dispersive system. As we take a look at the session graph, you can see there are 3 channels that make up the single session of data transfer. We're using a combination of these 3 deflects that have been optimally selected based on real-time current network conditions. What I'd like to do is demonstrate the self-healing capabilities of the network. We're going to manually remove one of the current in-use deflects from service. This could simulate a DOS attack, a replay attack, network congestion, a latency spike, any number of performance or security reasons that would indicate to the system that the path is no longer optimal or secure. You can see that the system immediately spins up 2 new green paths, and 2 of the previously green paths move to the orange dropping state, indicating that they're no longer in use. The system is able to autonomously detect issues and route around them in real time without stopping the file transfer that was happening, as you can see on the left-hand side of the screen. From an end-user perspective, data continues to flow and the system continues to work as intended. We'll take one final look at the side-by-side comparison between the two systems. You can see that the VPN system is at 2 going on 3 file transfers, and the dispersive system is at 18 going on 19 transfers. Even though we're using a highly secure protocol, we're approximately 9x faster in terms of overall throughput and data flow. In conclusion, the dispersive solution offers a handful of advantages over a traditional IPsec point-to-point tunnel solution. Active-active multipath transmissions allow for highly obfuscated transfer of data. Data deflects bring resiliency and autonomous self-healing with intelligent routing decisions. The solution architecture allows for increased throughput and bandwidth, and the final result is a high-performance military-grade security solution from end to end.